Well, all right, everyone. Welcome back to Math 221. Hope your weekend went well. Let's get this started by taking a look at two different graphs. Okay, so we'll have one, maybe like that. It's not quite aligned to the dots, but it's close enough. And here's two graphs that I want to take a look at. One looks like this, it's increasing, right? And here's the other one. It's also increasing, but there's a definitive difference between them. And I want to try and use this lecture to spell out uh, the differences between these, okay? And as I said, they're both in increasing, right? They both have tangent lines with positive slope, um, but there is a difference. In order to sort of tease out that difference, one thing that we can do is we can actually draw a couple of tangent lines, okay? Maybe we have this one, maybe that one, and then say that one. Okay, and there's a couple things that we can sort of notice about this, right? One, our graph is sort of always sitting on top of the tangent lines, right? As opposed to if we go over here um, and draw some tangent lines, maybe we'll start with that one. We'll draw three again, call that one number two, and then maybe call this one number three. Okay, so as we said, this one, our graph is sort of always sitting on the top of the tangent lines, right? And then over here, our graph is sitting on the bottom of the tangent lines. But another thing to notice here, right, is that the slope of our tangent lines here are increasing, right? This middle one is steeper than this first one, and the second one is steeper than the third one. Or the third one is steeper than the second one. Here on the right, though, our first tangent line is the steepest, and they sort of get shallower, right? And so if we then take that to think about how these tangent lines represent our derivative, that means that for the one on the left here, it's increasing, and the way that it's increasing is increasing, right? Or the speed that it's increasing is increasing, right? Whereas here, over on the right, we're still increasing. All of these tangent lines have a positive slope, but we're increasing at a decreasing pace. Okay. The other thing to sort of notice about this, right, is this graph sort of opens upward in the same way that like a parabola opens upward. And this one is sort of facing downward in the same way that that a downward parabola faces downward, right? And these two notions of, which way it's facing up and down, um, sort of give our definitions of these ideas, okay? And let's jot down those definitions, okay? So let's grab ourselves a differentiable function. So let f be differentiable on AB, right? And then we have two definitions. The graph of A, or the graph of F, is concave, it's not high spell concave, C-O-N-C-A-V-E, up or upward on AB if F prime is increasing on AB, okay? And a similar definition, the graph of F is concave downward or concave down if f prime is decreasing on AB. Okay. And if we turn our attention back to these, first two, here our derivative is increasing, so we're concave up. Here our derivative is decreasing, so we're concave down. And then much like when we were talking about last week, increasing or decreasing at a point, right? We can also think of some graph being concave upward or downward at a specific number, right? X equals C, if you can find some little interval around it, right? That's sort of the same idea. Okay. Also connecting to last week, right? Remember, we looked at how to tell where a function is increasing or decreasing using the derivative. And now we're looking at whether or not a derivative is increasing or decreasing. Okay. And this is where it's really, really nice when our function's derivative has a derivative, right? This is where the second derivative comes into play for functions where it's defined, of course. Because f prime is increasing when f double prime is positive, right? And f prime is decreasing when f double prime is negative. Okay, and this actually is the content of our next theorem, right? And the proof, while I'm not going to write down formally, the logic to prove it is actually just right there, right? And it says this, right? If the second derivative of f is positive, say for all x in some interval a, b, right? So for any x in this interval, the derivative is positive, then the graph of f is concave up on AB, right? Similarly, just like we said, if f prime of x is less than 0, our second derivative is negative. Once again, for all x in some interval AB, then the graph of f well, we have our second derivative is negative, so that means our first derivative is decreasing, which means we're concave downward. Or just simply concave down on AB. And so with the content of this theorem, let's do some examples, okay? Let's turn our attention to a function that we worked with a little bit last week, x cubed minus 3x squared minus 24x plus 32. And we want to look for where this guy is concave up and concave down, okay? And in order to do that, we'll first take our, first derivative. We'll get 3x squared minus 6x minus 24. And then second, we'll take our second derivative. Looks like we'll get 6x minus 6, okay? Or if you prefer, 6 times x minus 1, okay? And so our second derivative is defined everywhere, which is great, right? So we can use that theorem. And indeed, we can throw together these kind of things that we use for the first derivative test. But they're going to be pretty simple, right? Because this is a line, right? At 1, it's equal to 0. If you feed in something bigger than 1, say 2, 2 minus 1 is positive, times 6 is positive. If you feed in something less than 1, say 0, you get 0 minus 1 is negative, times 6 is negative. And so that means that we need to be, well, negative on this whole interval and positive on this whole interval. And so that means that we can write f is concave up on, well, everywhere this is positive. So 1 to infinity. And then f is concave down on negative infinity to 1. Okay, with these polynomials, it's not too terribly difficult. Okay, so let's look at something that's not a polynomial. Right, another one from last time. Let's in this case set f of x equal to x plus 1 over x. Okay. Well, if you don't remember the derivative of this, we can take it again. The derivative of x is just 1. The derivative of 1 over x is the derivative of x to the minus 1. So my minus 1 drops down. We subtract 1 to get x to the negative 2, or 1 over x squared. Okay. And then I can do that, right? Move the negative over. But we do need a second derivative here to look for where it's concave up and concave down. My derivative of a 1 is just going to go away. And then the derivative of x to the negative 2, well, my negative 2 is going to drop down, but then it's going to cancel with this negative 1, so we're just going to get a 2. And then I need to subtract 1, and we're over 2 over x cubed, right? Or 2 times x to the negative 3. Once again, we can draw our little number line, and we're going to be right here at 0. But we notice our function doesn't exist at x equals 0, which isn't necessarily a direct problem, but it is something that we ought to be aware of. Okay. But since our function is continuous everywhere else, right? Just this is the same logic we used last week, but since our function is continuous everywhere except this single point, then as soon as we can, pick a specific value on each of these intervals, we're going to know whether the function is positive or negative on those whole intervals. And so we can just pick something simple like 1, right? 1 cubed is 1, 2 over 1 is 2. So this is positive, right? All of this is positive. Okay, well, what about here, right? We can pick a negative 1. Well, negative 1 cubed is negative 1. 2 divided by negative 1 is negative 2. So all of this is negative, right? And that means, right, our graph of f is concave down on negative infinity to 0, right? Because we're negative all the way here. Since our second derivative is negative, our first derivative is decreasing, and since our first derivative is decreasing, we're concave down. Similarly, f is going to be concave up on 0 to infinity, because our second derivative is positive, so our first derivative is increasing, so we're concave up, okay? And now our mind sort of shifts to what's happening in between, right? Say you've got some function that models, maybe your, dollar spent on advertising here and your sales here, right? You might expect the graph to look something like this, right? Where this doesn't actually decrease, maybe it continues up that way, okay? And I want to turn our attention to graphs like this because I think they'll be fairly instructive. And here's the idea, right? As you start to spend more on advertising, people are going to know more and more about it. And, your sales are going to increase. And then you're going to start running into diminishing returns, right? And the question, of course, is when do these diminishing returns take over? And you might notice, right, your guess, right, for when diminishing returns would take over would be right here. But something I want you to notice is that this graph, this part in green, this is all concave up. This part in purple, this is all concave down. Right? And this point in the middle, sorry, that should say concave up. This point in the middle here, right, we call this a point of inflection. Okay. And the point of inflection, it's where we switch from, increasing at an increasing pace to increasing at a decreasing pace. Okay, let's sort of firm up this definition. Okay, so we'll say a point on the graph of a continuous function we'll call this function f, where and we need two conditions here, where the tangent line exists and where the concavity changes is called a point of inflection, right? Or sometimes called an inflection point, okay? And I'll give you three little graphs to sort of give examples of what this could look like. And what I want to draw your attention to, sort of while I'm, drawing these examples, well, is that when the concavity changes, right, that means the sign of the second derivative has to change, which of course then means that the second derivative needs to equal 0, right? And so, we're looking for the behaviors of the zeros of the second derivative, right? That's one of the reasons in pre-cal why, we hit so hard on finding the zeros of polynomials, is that it allows us to do this type of analysis, okay? But let's take a look at some of these, right? This is here first on the left. This part of the graph is going to be concave upward. This part of the graph is going to be concave downward. And right in the middle, we're going to have this point of inflection. And I want to draw your attention to this tangent line. It's not 0, right? This tangent line is non-zero, right? You sort of might first expect that, oh, well, if my second derivative has to equal 0 there, then my first derivative has to equal 0 there. But it totally doesn't. But it does mark a change between, tangent lines that are increasing in slope and tangent lines that are decreasing in slope. Okay, let's take a look at this second one. Well, we're concave up here, right, until about, looks like about there. And we're concave down here. And right in the middle here, we have our point of inflection. And we do have a horizontal tangent line. That's one of the reasons why the first derivative test would sometimes say it's neither, right? Because sometimes that first derivative is zero because you're at a point of inflection. Taking a look at this third one, we're concave downward here, we're concave upward here, and our point of our point of inflection is right there, believe it or not, with a vertical tangent line now, right? And at a vertical tangent line, it's important to note the first derivative does not exist, right? But there's still a point of inflection there because the tangent line exists. And we can totally meet graphs like this one. This zero here is not a point of inflection, right? We'll worry about graphing this here in a bit. And we'll see there that it isn't, precisely because there is no tangent line to f of x equals x plus 1 over x at x equals 0. The tangent line simply does not exist. Whereas in this instance, the first derivative doesn't exist, but there is a tangent line there. Okay, so let's sort of, run through the steps of finding some points of inflection. Okay, we'll start with something simple, right? And we'll start with just say f of x is x cubed, right? The first derivative is 3x squared, and the second derivative is 6x. What I want you to notice here, right, is that, all of these functions are continuous everywhere. There are nice little polynomials. And if we draw our little diagram, right, we have a 0 of the second derivative at x equals 0. Right? Our function is 0 here. And if we're negative, well, then 6x is negative. And if we're positive, 6x is positive. Okay? And so what that means, right, because our function is continuous, its tangent lines exist everywhere, and we have a change in slope here. And since we have a change in slope here, right, that means that f of x has a point of inflection at 0, 0. Okay. What I want you to notice, however, right, to be very, very careful, is just because we have one of these zeros doesn't mean we have a point of inflection. And a fantastic example of that is actually x to the fourth. Okay, here's what I want you to do. Pause the lecture and sort of run through in your mind, maybe on a little scratch piece of paper really quick, why x to the fourth doesn't have a point of inflection at 0, 0. Because its second derivative does absolutely have a 0 there. Okay, but let's turn our attention to our next example. Okay, let's say g of x is x minus 1 to the 5/3. Okay, so take your number, subtract 1, put it to the 5th power, take your cube root, and now we'll take its derivative. We can use the chain rule here, right? One of the things that I think you'll notice is when we first started doing the chain rule, right, we were writing down our u's and our u primes and all of that. And then over time, as you get comfortable, some of them, you can start to do the chain rule in your head, right? We have this function to this power, right? So we can bring down the power and keep the function and then subtract 1, right? So that now it's going to be 2/3. And then we need to multiply by the derivative of the inside. But the derivative of the inside is just 1. So we're good, right? This is our derivative. But now we need to take a second derivative, and things are going to get slightly more interesting. Our 5/3 is going to factor through. We can actually follow the same idea. We're going to bring down our 2/3. 2 times 5 is 10 over 9. And then we still have our x minus 1. 2/3 minus 3/3 is a minus 1/3, right? And then we need to multiply by the derivative of the inside, which is still 1, okay? And we can write this as 10 over 9 times the cube root of x minus 1, okay? And now we're interested in looking for zeros and where this guy isn't defined. Well, it's not going to be 0 anywhere, right? Because it's only zeros are going to come from the numerator. But if we see where this equals 0, this is going to equal 0 when x equals 1, right? So we have a problem at x equals 1. We can jot that down on our little guy. And at x equals 1, our function does not exist. Okay, well, last time we saw this, it didn't work out very well. But let's continue to push through. Okay, well, let's pick something positive here. We're going to pick something positive here, right? And it's very easy to just pick 2, right? If you pick 2, then this term comes out really nice, right? You're just taking the cube root of 1. But I actually want to show you what happens when you pick 3, right? And sort of run you through some logic that's going to be helpful in the next part, right? 3 minus 1 is 2. Now, the cube root of 2, I don't know off the top of my head. My guess it's going to be somewhere between 1.2 and 1.3. But what's important is that it's positive, right? Because then when I multiply it by 9, it's still positive. And when I divide a positive number by a positive number, it's still positive, right? And you can sort of work through these pieces of logic without actually having to calculate the full value, as long as you're careful. Similarly over here, right, I could pick, 0, and things would go through pretty smoothly. But what if we pick -1, right? -1 minus 1 is going to be -2. The cube root of -2 exists, right? It's the negative cube root of 2. And okay, well, negative cube root of 2 times 9 is going to be a negative number. When I divide a positive by a negative, that's a negative number. So that means along this whole interval, we're negative. Okay, so that would tend to point, right, that I might have a point of inflection at x equals -1, right? Because we're going from negative to positive. So since our concavity changes here, as long as our tangent line exists, well, then our function's going to have a point of inflection there. And how can we test if a tangent line exists? Since the domain of G is everywhere, right? No values fail, well, then x equals 1 is in our domain, right? So, since x equals 1 is in our domain, right? G has a point of inflection at 1, 0, right? Where you can get the value of G out of there pretty quickly.